A little bit more with verification, validation. Here you have some links, at least, where you can find databases from huge simulations, DNS, and also large eddy simulations, that you have something to compare with. CFD Online, also a very huge database for you for a lot of information. And also here you can post questions and get answers within reasonable time. So people are quite active on the CFD Online. So that one definitely can be recommended. I'll put out this PowerPoint presentation for you on the homepage, so you can find it there and then have these links. Journals, of course, we have a whole bunch of them. Libraries filled with journals, so it's a lot of information to you can find almost anything here. Input, what should you have as part of your documentation? The short version, all information that any user needs to reproduce your simulation. That's what you should provide. So you see, you have to give him a lot of information if he wants to do the same simulation as you have done once more. Yeah, verification study, important of course, but not necessarily the easiest thing, but definitely something you have to address. You sort of have to convince the reader, my results are good, they are correct. Some recommendations here, they are not necessarily 100%, but say recommendation. Smooth grids, always an advantage. So in the old days we said the cell volume from one cell to the neighbor shouldn't differ more than 15%. That was the old rule. Now these codes have been stronger, so yes, you can have larger differences in volume from neighbor cells, but the more smooth the better. Large enough domain so that the input-output values don't influence the results too much, at least. Don't use a totally crazy mesh. Totally crazy meaning you have cells triangles, that will be nice, a nice triangle, and then you have a very small one next to it. Not so bad, not so bad, meaning not so good. So he can handle it, yes, but try to avoid it if possible. So here I would then have split it up actually into more cells, at least better, maybe even something like this, to have a more smooth resolvement of the space. Also remember this correction number that we had for meshes when they are not perpendicular, all the mesh lines. Grid refinement in high gradient regions. Of course, you need a lot of resolution if you have a lot of actions going on in narrow spaces. 10 points in the inner layer, as you know, expensive. And for high Reynolds number, you can't do this, hence wall models. Check the grid quality. That's not too much in OpenFlow. This is, I think it was actually been written for Fluent. Then they had some tools to check the grid quality. We have something in in OpenFlow that you should be aware of. You have something called check mesh, and he should report mesh OK. He can report so and so many warnings. If you have a very highly distorted mesh, then check mesh will report, you should try to smooth out your mesh a little bit better. Evaluation of uncertainties, that's a hard thing to do, but at least now you have been taught a little bit about verification and validation. Doing a parameter study, expensive, but it might be part of your project. Say you are really uncertain what the turbulence level on the input should be. Say for the K and omega values, for instance. Then you should run a parameter study, trying with one value, trying to change it with 10%, 20%, 40%, and see what the influence on the result might be. Then you have a parameter study, and then you can say it is so and so sensible or sensitive to this parameter, and hopefully then you have something to compare with to say that the best input value is 2.5 and not 2.6, for instance. Things like that, sensitivity analysis as well. Used approximations, don't ask me what that means. Anyhow, that should be the end of it, I hope. Yeah. Okay, as I said, I will put that one out for you, so you will have an option to see it for yourself and look at the different links. Okay, any questions before we continue? So a little bit more today, but that will be now more tips, ideas that you can, if you want, use to play around with as a part of your project, your group work. We can start with what should we start with here? Paraweather. I had a contact from the industry, paraweather.no. I think it's one guy from Bodø, his entire company. He has an idea and a dream. He wants to build shelters for refugees. And the shelters should then be light, 20-30 kilos, and should be very easy to set up. And they should be strong enough then to hold for, say, some months, and should be big enough to cover an entire family. You can read for yourself. He's worried now. How should it be made? What's the forces then acting on such a tent when the wind comes? Of course, the potential theory you should all know. Here you will have high velocity. Down here you will have stagnation pressure. So if you have an opening here, you will get high pressure inside the tent and low pressure up here. The tent will be destroyed by the wind. So what you should have is close here, and then you make an opening up here. Sadly, then you get rained on, so that might be a bad idea. But maybe you should put in an oven or something, I don't know. Then you could have a low pressure inside the tent. Then the more it blows, the stronger the storm, the more forces is actually acting down on the tent instead of up. Things like that. He's very interested in helping him designing the shape of these tents. So if any of you are interested, I can give you his email, and then I think he will be here tomorrow and talk to you and have some input for you. He's very eager that we look into this problem. So that would be one topic. Also here, it's a question then, not only the shape for one, but say you need 500 of these in an area. How should they be organized? Should they be close to each other, far from each other? Should they be organized in equal rows, or should they be randomized so that the vortex shedding from one doesn't destroy the tent behind him, and so on and so forth? So that's one option for you. Another place, if you have no idea, if you write in Google, you write OpenFlow, and then you write honey, you should get the source code for a course in Chalmers. So that's actually quite interesting web page. The source here, the official, yeah, where is it? You just add a different year if you want to have a look at, say, the last year's. So then you just do it like this, I think. Copy and paste, and then 15. Yeah. Then you have the course from last year. Then you can read a lot here if you like, but what's interesting was down here somewhere, student reports and tutorials. Here you have a lot of information. Here you can find setups, you find the finished reports, and also you find all the files, all the input files. So if you find something interesting here, okay, then you have the input files. You are up and running tomorrow. So beautiful. Please don't steal the report, then that would be too boring, but at least you have a flying start here. You can really have something up and running very fast instead of have to do everything yourself. And then I think he has done this course for several years, so you can go back 14, 13, 12 and so on and find different reports all the time. So definitely something worth looking into. So that was Hani. That's the name of this guy dealing with this OpenFlow course from Chalmers. Another one you could have a look at was what was it called? SimFlow. SimFlow. No, not SimFlow. Have they gone commercial? No. That was strange. Sim minus flow. Okay. They have created sort of an umbrella over OpenFlow, and here you now have a free license you can play around with for Windows if you want to use OpenFlow a little bit easier. So they have sort of designed a graphical umbrella. So here you have both pre and post processing to actually do a lot of things. So this is also something that you can play around with if you want. Last year we were able to get a license for this one for free, and I think we can do it again if you're interested. Just tell me and I can see if we can get contact with this company. So feel free to have a look at this one if you yeah, would prefer a better graphical interface than sitting and text editing all these block mesh dict files and control dict files. Finally, I wanted to show you something with MATLAB. Something I found on the web, which is quite interesting. It's a MATLAB script that produces unstructured meshes. And from this mesh, it should now be possible. This is something I'm willing to help you with. Saving this one as a file that OpenFlow can read. So you can play around in MATLAB, creating the mesh here, and then we can import it into, yeah, thank you very much, that we can play around with in OpenFlow. And some of these meshes, you see, can be quite sophisticated. Here we want to resolve the close to the boundary, for instance. Any geometrical shape, ellipsoid, and here, here, an airfoil. Here you might wonder, why have they chosen a circular domain? Why not have it squared, sort of input-output symmetry lines? Well, the reason is, for airfoils, you are typically interested in this angle of attack, the alpha. And then you want to change the alpha and see the lift and drag coefficients. That's typically what you do with an airfoil. But depending on the alpha, so if this one now is the angle of attack, that means I have my inflow here. And yes, I can construct a mesh here and then set up an inlet and then an outlet. Shouldn't be a problem. But if I want to change the alpha, then I have to change the entire mesh. But with this trick, you actually say everything here is an outlet. But then you give him an initial value depending on your choice of direction here. You say initially everything then is set to be 10 meters per second in a certain angle. Then depending on the angle that you choose, this angle for instance, then this part of the boundary will then be automatically an inlet, and the other one will automatically be an outlet. So here, very easy to change the angle of attack without moving the mesh at all. Very easy. And here, of course, very interesting to zoom into the nose, for instance, to have a really nice, smooth mesh resolving the details. So if any of you would be interested in using this this tool, designing your own mesh, tell me. I have written some MATLAB codes already that can do sort of writing these meshes here into at least a fluent mesh that we know can be imported into OpenFlow. Also, when that is possible, we have another option. I don't know if you have tried this one. PDE tool in MATLAB. It solves partial differential equations using a finite element method. So here you can now construct whatever you want, an ellipse, and then you create a mesh, and then you say I want a finer mesh, or I even want a finer mesh. And then you have to now in tool here, you have to decide what partial differential equations you want to solve, what are the boundary conditions, and then find a solution. So you could solve it all the way here. But Interesting part here for me would then be to use this as a grid generator in MATLAB. Here you have some options. You can play around quite easily with a two-dimensional mesh, making a mix of squares and blocks and circles and ellipses, whatever. And then just click the button, create the mesh, and then as an option should be here, or was it file? Save as. So you can export this mesh into MATLAB, finding all these triangles, all the geometries, and then again saving it as a fluent mesh, which then can be imported into OpenFlow. So I would be interested in if some of you would jump on such a task, playing around with MATLAB and designing grids here and then importing it into OpenFlow. That would be very, very interesting for me. Okay. Then actually I don't have anything else for you today. I can show you the last thing. Where was it? No, it's not here. Here we are. Now what? I want to open it. Can't you do that? Okay. There we go. Multi-phase exercise number 6, the last one I will give you, I think. So this downbreak case we have already seen. At least we have run it. We also played around with using several processors here. So what I would ask you to do here, play around with different meshes. This is a laminar case, so it should here be possible to find a grid-independent solution. So try finer and finer mesh. You have a command called refine mesh minus overwrite. Then he will sort of double the mesh in both directions automatically. So that's fairly easy. And also then if you look at, say, this image and say focus on this little droplet that is here. How will he change when you change the mesh? Is this correct? Should it be one droplet or maybe several? I don't know. So you use that one as a sort of a predictor, something that we sort of now should validate or verify that yes, it's supposed to be like this or should not be like this. I don't know. Play around with it, finer and finer mesh. Also, it's only after 0.25 seconds, so you don't have to simulate for so long to get this this image. As a second test, use say a very simple geometry here. The square cavity test case, 1 by 1 meters, and then initially you put all the liquid up in the ceiling. Then you have air here and water, and then as you start, he should fall down. Of course, he will have troubles falling. I don't know if you have tried this trick. I won't do it here. You take a glass of water, you fill it, and take some paper, thin paper, newspaper, just a small piece, and then you cover the opening. And then you do it like this, and then you let go. He doesn't fall down. I mean, he's stuck. Same will happen here. Initially, when you try this simulation, and if you have not atmospheric opening, but it's a solid wall up here, he will have trouble starting to fall, because it will be a vacuum behind him, so he won't fall. Of course, he will, at least if you have some 20, 30, 40 cells here. He will eventually start to fall, but it will take some time. Just have a look at it. My question is, when he has fallen down and sort of settled at rest down here, have we lost any water in the process? Is this area here the same as we will end up with as time goes to, not infinity, but a long, long time? Here you might want to cheat during the simulation. First it's going to, well, take a little time, and then he falls. Then you have a lot of action, a lot of dynamics that you have to sort of resolve in time. But then he will sort of settle and have some slow wavy motion here. That's going to take forever before they die out. So there you might think of cheating, meaning you simulate, say, 10 seconds. Then he should have fallen down and start sloshing around down here. Then you stop the simulation, change, say, the viscosity, and then continue. So then you can make him much more viscous. Then he should settle much faster, for instance. But play around with it, see what you can make of it. He should be quite conservative. You shouldn't lose mass during this simulation, but test it. So that's the task. So we can play around with that one tomorrow, or up to you then. If you have questions regarding possible group work, project work, then we can have a discussion there. Okay, any questions? Then we stop here.